what's the shortest? This way, everybody actually got to answer it, right? That's the idea, not just the people who already know the answers. And you know whether or not you know by the end of this, okay? And as I said, I'm only going to use this for attendance. Okay, so if you actually did it, you're fine. If not, obviously you didn't attend the class. But also it's useful for you to get a feel for whether you're following or not. And I might actually do this more often. But let's see. Anyway, this is important because last time, I recorded the class and some of you actually heard it. You may or may not have heard it. And I'm going to continue that class today, so I don't know. Anyway, so what's the shortest path from A to G? ABG, okay. So basically give a 1 point if people wrote that, okay? It's not yours, you're looking at the other person, just put a 1 point there. If you wrote something like ABG, okay? What's the cost? 8. Okay, if they wrote 8, just put a 1 point there. What is the highest value of h of b? The highest value h of b can take without violating admissibility. That's a curveball. I mean, obviously, it extends its complexity. So what should be the highest value h of b can take without losing admissibility for the heuristic? 16. H of b. So how many people are saying, so somebody said 16. Okay, so what's the reason? Let's actually, by the way, let's play this game. I'm assuming that the first time I heard about it, I had all sorts of crazy misimpressions about heuristic. So it's okay to bring them out and then cut them out. Okay, the few people who got it are fine. So why do you think it's 16?
Heuristic is the distance remaining to the goal. So
yeah.
You can go from B to C and C to G. So
yeah, but you can also go directly from B to G.
Yeah, but it's the lowest cost, right? 3.
Okay, so that's, so the heuristic is the estimate on the lowest cost. When we talk about cost, so for example, when people ask you what's the distance between Tempe and Los Angeles, they don't ask, they only ask shortest distance. Okay, obviously you can go from Tempe to Los Angeles by first stopping by in Jerusalem and then coming to Los Angeles. That would be a path, but that's not what we are interested in. So we are only looking for the estimate on the shortest path. Okay, so what is the answer? Give me another answer. 3. Okay, so if you are ever more than 3 for h of b, then you are in trouble. Okay, so again, if somebody wrote 3, give them 1 point for now. That's all. Okay, here's my question: how many different values can h of b take and still be? So what are all the possible h functions that you can write for h of b such that it will still be admissible at b? What are all the different values you can give for h such that it will still be admissible? Okay, so how many values?
0, positive, less than 3.
So how many values?
3.
Infinite.
Yes.
I just hope you understand that. Costs don't have to come in round miles. Okay, so there are infinite number of values h of b can take and still be admissible. There are also infinite number of values it can take and be inadmissible. The lowest value h of b can take is what? 0. Is that because of admissibility or something else?
Because there are no negative edges.
We are not allowed negative edges. Do you see what I'm saying? So the reason h of b can at the lowest be only 0 is not because of admissibility. Because if h of b is minus 17, that will still be an optimistic estimate on the distance to go. The only problem is with minus 17, you are violating a different rule, which is that all edge costs, basically heuristics have to be positive estimates. Okay, so that's 3. What about h of c? What's the highest value h of c can take? 7. Okay? So if they wrote 7, give them 1 point. Okay. What is g of n1? So basically, I was asking you to start with n0 a and do search, and you get n1 b n2 c, and we need g h f values for all of these. Okay, so what's the g value for n1? What is the g value for n1? 5. If you write 5, you're okay. How about g value for n2? That's 7, yes. Okay, so, and then how about h value for, I already gave you, h of b is 2, h of c is 2, so h value would be 2 and 2. And what would be the f value?
7.
This will be 7, this will be 9. So on the queue, how will they be placed? So you would put n1, whose merit is 7. Okay? And then n2, whose merit is 9. Okay? And then, of course, next you will pick n1 and expand it. Fine? That's what you're going to. Yes, sir?
Can you explain admissibility again?
Admissibility is the, so as I wrote earlier, okay, this is fine, we'll do it here. So admissibility is that for all nodes n, h of n is less than or equal to h star of n, where h star of n is the true shortest distance from n to the goal. From n to the goal.
So the largest h of n that's admissible would always be
H star, exactly. Largest admissible heuristic is indeed H star. We'll actually look at it in a minute, but that was the discussion that we had last time. So if you really, between two heuristics, you know, if one heuristic is bigger than other heuristic in all the places, in some sense it will do less search. Okay, and you can see this by actually making heuristic to be infinite everywhere. If you make it infinity, you do the least amount of search. This was the point I was making in last class, that if you just assume that, my God, I have so much work to do, then you don't have to do anything, right? I mean, if so much work to do, then it's not worth doing it. Okay, so if you overestimate as the work left to do is infinite, then you will basically stop doing anything. That's exactly what happens here too. So as h keeps increasing, the search effort reduces, but if h crosses h star, then you are no longer guaranteed optimality and completeness, right? Because essentially there may be a solution, and you just, because you're being so pessimistic, you are not actually finding it. Okay, so optimistic heuristics always are guaranteed to be optimal and complete. But there is optimism and there is delusional optimism. Delusional optimism is h equal to 0. So, the guy who thinks, I have nothing to do, I'm sure I'll be done, will basically assume that all states are equally far away from G, and they're all actually 0 away from G. And if you do that, you're essentially doing uniform cost search. Right? Okay. So, so this basically, if people got the f values 7 and 9, give them 2 points. If not, just give 1 or 0, and then add the numbers, put the total, put a circle around it, and show it to the person and then pass them on to me. Okay.
Can't the H value be one lesser than the second highest one and still be admissible?
It can be any number of values.
No, can't it
Okay.
need not be the
Silence, guys. Yes.
it need not be the shortest. It can be lesser than the second shortest. But
What does it mean? What are you talking about?
so H value
H value of what? Who? Tell me.
of B,
Of B.
can't it be 15?
Why should it be 50?
Because it will still pick the.
No. Okay, so here is the deal. If heuristic is admissible, you are guaranteed to find optimal solution. What does that mean if the heuristic is not admissible? You might go wrong. Okay? So I can give you a large number of inadmissible heuristics, which you will actually wind up getting optimal solution anyway. That's because you just lucked out on that particular inadmissible heuristic.
No.
Okay, so for example, if you drive drunk, you won't necessarily get into an accident. Okay? It's just that you don't drive drunk, you have much less chances of getting into an accident. So its admissibility is a sufficient, not a necessary, but a sufficient condition. And for optimality, saying, I'll come up with a solution, why don't you check if it's optimal or not? Yeah, whenever you feel like saying it, hit yourself on the back of the head. Because that's as good as saying, you do the work yourself. I wasted your time. Okay, so your point is very well taken. If I can give 15 as a heuristic for B, and you will still probably find this as A star will still find this as the path and will end. That doesn't disprove what I said. What I said is admissibility is a safe policy. If you are admissible, you are guaranteed to be optimal. If you are inadmissible, guarantee is not there. In fact, one of the interesting things that we'll talk about is oftentimes finding admissible heuristics that are also informed is very hard. And so in practice, I have this thing, I don't know whether I said it in the class or not. The difference between a programmer and a computer scientist is a computer scientist first figures out what are the requirements to have good properties, completeness, optimality, and then gives them up. Okay, because it's just too hard to ensure optimality. Okay, so you give it up knowingly. Programmer doesn't know, doesn't care. Do you understand what I'm saying? Okay, so it's not because just because you're a computer scientist, you're not required to only produce optimal solutions. If your producing of your optimal solution takes 65,000 years, then nobody wants your solution. Okay, so you want to understand what are the properties that heuristic should have such that the solution will be guaranteed optimal. And many a time, that's basically the property is admissibility. And many a time getting very good quality admissible and informed heuristics is hard. Remember, admissibility by itself is cheap. H equal to 0, admissible. You can always get admissibility by just saying, I'm already at the goal probably. Over-optimality never killed anybody. Not in terms of quality of the solution. It kills them in terms of the search time. Okay? But if you want admissibility as well as informedness, then you're trying to get H star as close to H star as possible. I'll show this picture in a minute, but suppose I have something like this as H star. Okay? If I have one heuristic here and one heuristic here, clearly this one, H1, is better than H2. But H1 is still much worse than H star. Okay, here is another heuristic that is H3. H3 is going to do significantly less search than H1 and H2. But it crossed over the limit. It crossed over H star. If it crosses over H star in one point, guarantees are off. All I'm saying is I won't give the guarantee. You have to find the guarantee yourself separately. Okay? Now, many a time, this may be a heuristic that you would like to use. In fact, when we get to the next part, which is like doing state search and planning problems, we'll point out that most existing planners actually use inadmissible heuristics, which looks kind of sad. You know, why develop a theory if you're not going to actually follow the theory? And that's why I want you to understand that the difference between a computer scientist and a programmer is one knows what it means to get the right property. You know, you're being stupid if, in fact, it's so cheap to get that property and you still ignored it. You're also being stupid if, in fact, getting that property will kill the ability for this algorithm to get done in any reasonable time. Okay, so that's what we're trying to do. So in this case, many a time we will look for heuristics like H3 in practice, which are no longer guaranteed to produce optimal solutions. But then what would people do? Then use H3 and will then solve a whole bunch of benchmark problems and say what did H3 find as the optimal solution, and also actually find the real optimal solutions by using H equal to H0, H equal to 0, or some other known admissible heuristic. That would take much longer time. So you have solved these problems in the past once, so you know the exact optimal solution. You compare the true optimal solution to what H3 found, and then you say, notice that H3 isn't too much off. That's what people do actually. But you will never be able to tell when you are optimal, when you are not optimal. The only time we can tell for sure is if H is guaranteed to be below H star across the board. If you make it not below even 1 point, I can construct an example where it will come and bite you. Okay, so it's a subtle concept. Okay. Okay. One other thing. Okay, that's fine. So are there any questions, any further questions on this, on what we just discussed? Okay, if not, let's actually start. Continue. Please make sure that those are given back to me by the end. Since you now have yours, you should give it to me because that's your attendance for today. Okay, not this. Why do you keep doing this? Yeah, that's the problem. Okay. Actually, what I want to do is one more thing I want to do without this. Okay. So, bring this back up again. Okay. So, here's one more question since we're talking about admissibility. I have free space. Okay, a robot is basically trying to go from here to here. Here is start state, here is goal state. Okay, you do know that there is an admissible heuristic in this kind of scenario. The reason robot will have trouble in these cases is because there are funny looking obstacles all over the place. And it needs to avoid the obstacles and go to the goal. Right? So you do know that the shortest, so basically, suppose this is a grid, and so there are points in the grid, and it's trying to go from one point to other point to other point. Right? So my question is, so suppose I'm at this point, I need the heuristic value. What would be an admissible heuristic? The guy who is looking at the cell phone, don't do it. Okay. you can leave the class and do it. That'll be completely fine. Okay, so what is the, how do you get an admissible heuristic here? Straight line distance. Straight line distance is admissible. You agree with that, okay? Now, it's okay. I mean, h equal to 0 is also admissible, right? And h equal to straight line distance is way better. But I actually want to do better than straight line distance. Remember, the trick of reducing search is being pessimistic about work left to be done. Trick of ensuring optimality is not to be over pessimistic. Don't overestimate it beyond how much work is left to be done. You see, that's the straight and narrow path. Okay, so clearly straight line distance is more pessimistic about how far it has to go than h equal to 0. And yet it is less than the true distance. That's why it's admissible. Okay, so I want to now consider two different ideas. Okay, here is an idea where I will put a circle, the biggest circle that I can, the closest circle I can put around these obstacles. Okay, and then I'll try to basically find, as my estimate of the shortest path. Essentially, from here, I can essentially talk about tangents, right? And then I will go through these tangents to G. And it's a little costlier than computing the straight line distance. Okay? Costlier than computing the straight line distance. So, if I put circles like this and compute the distance, it will be higher than straight line distance. In some sense, you feel as if it's going to be more informed because it's actually more taking the, taking the obstacles into account. Here's my question. Do you think this would be an admissible heuristic?
Need not be.
Because?
It's going to be greater than the actual distance.
Because it's greater than the actual distance. In fact, the best way to think about it is, suppose these two, there are two obstacles which are very close to each other, then the circles will be touching, so you don't have a path through them. So you think the cost left is infinite, but it's actually not infinite. And so it's not admissible. So we came up with a baby of an idea, and we found it doesn't work. So do we throw the baby along with the bathwater or find some way of keeping it? I want circles. I like circles. I put circles around the obstacles. I circumscribed the circles on the obstacles. What if I inscribe the circles? Do you understand what I'm saying? Suppose I inscribed the circles. The biggest circle I can inscribe in each of them. The circumscribe is the smallest circle I can put around the obstacle. Okay? It's in the inscribing means the biggest circle I can put in the obstacle. That too is better than straight line distance, right? It's not as aggressive as circumscribing. But unfortunately, circumscribing is not admissible. You can lose optimality guarantees sometimes. If on the other hand you inscribe, you get optimality guarantees. So you thought about admissibility. Here is a classic example where circumscribing versus inscribing means the difference between admissible versus inadmissible. You see what I'm saying? Okay. We'll look at other ideas, but this is one interesting, connection to actual admissibility and how you are approximating. In general, what happened there is if you relax constraints, you are admissible. Okay? If you tighten constraints, you are not admissible. In that example, when we had funny-looking obstacles, if I put circles outside, I am tightening the constraints. I'm reducing the number of places the robot can go through. Whereas if I put circles inside, I am relaxing the constraints. I'm making the obstacle smaller than it actually is. Relaxation will always guarantee admissibility. Tightening doesn't. What is interesting, however, is both relaxation and tightening are cheaper than the true obstacle. Because the true obstacle can be almost fractal shaped. And finding the shortest path around it can be quite costly. Okay? So you sometimes want to reason with upper and lower bounds. Okay? What we are saying is you are allowed to deal with the lower bound because that's a relaxation, but not the upper bound because that's not a relaxation, that's tightening. Okay, so these are the intuitions you want to get about admissibility. Any questions? Okay. Okay, so I want to, we talked a lot about admissibility and we sort of convinced ourselves that this seems like a good idea, it should work, but I actually want to try and prove that if you have an admissible heuristic and A star search ends with saying here is a shortest path, it's guaranteed to be shortest path. Remember, these kinds of things can't be said case by case. You need to have a proof up front. Okay? And we will do the same sort of a discussion that we did for the uniform cost search. Okay? I'm just going to repeat it in front of you. And in essence, you will actually see why the lower boundness of the heuristic, that is the fact that the heuristic is optimal, the heuristic is optimistic, helps. Okay? And it's not a particularly hard proof, so it actually is nice to look at. So I went through and I came to NG, node NG. Okay? And A star search, assume A star search ended with this and said this is the optimal solution. Okay? So what that means is, remember, G of NG is some value. What is H of NG? What is H of NG?
0.
0. Can you have H for a goal node be anything other than 0 and still be admissible? No. Right? That's part of being admissible. If you don't know when the goal comes and bites you, then you cannot be admissible. Right? Okay? So all admissible heuristics, we are doing search with admissible heuristic. Okay? Now notice that, is there one admissible heuristic for a problem? In fact, in that little example we saw there are infinite number of admissible heuristics. So whatever proof I'm doing should work for all infinite number of them. That's the whole good point. We just look at the properties of the heuristic. Okay? So all we care about is admissible heuristic says for all n, h of n is less than or equal to h star of n. That's all. That's the only requirement admissible heuristic has. Except it's a pretty big requirement. It's for every node this condition is satisfied. Okay, so this is where I ended with G of ng, H of ng, and F of ng would now be nothing but G of ng. Right? Now remember, A star search has a queue which is sorted by F values. Right? And it always picks the node with the lowest F value to expand next. So now my proof for this is, let's look for a counter example. So let's do proof by contradiction. Okay, let's act as if, so your friend comes and asks you, how can you be sure? What if I can produce you an n dash such that that is the optimal goal? Okay? Now for your friend to be right, notice that g of n dash, okay, must be less than g of ng. This is the premise. Okay? Now you will say, well, of course, this is not going to happen because if n dash is on the Q at the same time as ng, then I would not have picked ng. I know arithmetic, right? Now, so g of n dash was already present in the Q when g of ng was present. And if you are right that g of n dash is less than g of ng, I wouldn't have picked this guy, I would have picked this guy. Fast proof. Unfortunately, that's not enough of a proof. The friend will say, well, you don't know, n dash will come later on. Actually, when you picked ng, n dash was not on the Q. Some ancestor of n dash, n double dash, happened to be on the Q. So he or she just pushed you one, step back. How do you know? Remember in general when A star search ends, there are many partial paths sitting on the Q. The best way to think of the Q is each node on the Q is the tip of one of these partial paths. Do you see what I'm saying? The partial path sometimes can also be a complete path. If it was also a complete path, then it's easy to prove because that complete path is obviously worse than this complete path. That's why you pick this. What if the partial path is really a partial path? Okay, then you need to just argue, the case there. So here, g of n double dash, we don't quite know how g of n double dash will compare to g of ng. Okay, which is compared to f of ng, which is g of ng. But we do know the following thing. G of n double dash plus h of n double dash is equal to f of n double dash. Right? And it must have been the case that f of n double dash is greater than or equal to f of ng. Remember the line of argument. Your friend said, no, this guy was not there when you picked ng. One of its ancestors, n double dash, was there. And you're saying, well, that's okay. If that is the case, then its f value should have been greater than or equal to ng's f value. Otherwise, why would I have picked ng? Unless the computer is doing arithmetic now. Right? So, f of n double dash is greater than or equal to f of ng, but then f of ng is nothing but g of ng. Because h of ng is 0. Okay? Now, what is f of n double dash? F of n double dash, as we said, is g of n double dash plus h of n double dash. Now, h of n double dash is estimate of this path. The true cost of this path is how much? No, the true cost of n double dash to n.
H star.
H star. Right? So we happen to also know, that g of n dash equal to g of n double dash plus h star of n dash. We know this. That's how the g's are connected. Okay, now, so going back here, you know that you're saying fn double dash is already greater than g of ng. You agree with this? Now, fn double dash is nothing but g n double dash plus h n double dash, which is greater than g of ng. If that is true, then if I replace h n double dash by h star n double dash, since h star is greater than h, it should still be greater than or equal to g of ng. Do you see the argument? Okay, you are already, so our intuitive way of thinking about it is, even if I'm being optimistic about how much work I have left to do, I already think this path is worse than this path. So the reality can only be worse, it can't be better. That's the advantage of being optimistic. Right? If you are optimistic, then optimistic about work to be done, the reality will always be worse. Well, normally it's not advantage in real life, but in search it's good. Do you see what I'm saying? Okay, so this essentially allows you to say now that Gn double dash plus Hn double dash, H star n double dash is greater than G of Ng, which then means G of n dash is greater than G of Ng. I mean, greater than or equal to G of Ng. Which is opposite to what your friend said. So I just disproved the friend. Remember that if in fact this as well as this are equal, then your friend doesn't have an argument. Because if you have two equal size shortest paths, any one of them is fine. For your friend to actually have a case, it must be the case that your friend said G of n dash is less than G of Ng, according to your friend. But according to logical consequences of how the search works, this is true, which is exactly opposite of this. Proof by contradiction. Okay, this is the proof. Okay, and now notice that the reason this proof worked is because when I could replace Hn double dash by H star n double dash and keep this inequality the same. Had it been the case that this is a pessimistic heuristic, then when you replace it by H star, this inequality doesn't any longer hold. That's why proof won't go through. This proof won't go through. And in fact, there is no other proof I can actually give you which will show that it's optimal. Any questions on this stuff? Okay? So again, the intuition that you want to keep in mind is by being optimistic about work to be done. You're being optimistic about work to be done in each of the nodes, and this is the true cost to come here. The true cost to come here is already better than the optimistic cost of going through this node to go to some other goal node. Then it's clearly the case of a bird in the hand is worth more than two in the bush. Right? You actually, this cost, the true cost here is already better than the optimistic cost here. So the real cost would only be worse than this. So that's like saying, you already have $10, and I say, why don't you come with me? I might give you, less than or equal to $9. Why would you come with me? Okay? If on the other hand I said, I might give you more than or equal to $10, you might be tempted. Okay, because you never know until you actually come with me whether I'll give you more or not. Okay, but if I already told you less than or equal to $9, then you know that it's never going to be better. Okay. Questions? Okay, I'm going to remove this. I'm going to go back to the slides again. I don't have to have it. But that's fine. That is the proof written on the slide. You can go through the steps later on if you want. Okay, but I just did it on the board. But that's wow. Okay, it's the same exact proof that we did there. Okay. Now, what is interesting? What this means is, remember when we were looking at uniform cost search? And another way of understanding its admissibility was to realize that uniform cost search starts from the start node and sort of searches in concentric circles. Okay, so it searches the periphery of concentric circles. And so if you found G here first, then that's because you didn't find G up until this concentric circle. So the first goal you found must be the optimal goal. That's what uniform cost search does. A star does the same thing, except the contours are no longer concentric circles. They can be funny shaped, which are biased towards the goal. Okay? So the best way to think about it is, A star might start like this. So the contours it is searching over are essentially biased towards getting you to the goal. When A star has h equal to 0, then it would just be like this. When A star is admissible, then it will be like this. And when A star has h star, then essentially the contours will directly go. There is no, in all these things, basically you have nodes that are not falling on the path to the goal that you are expanding. Anytime you expand a node which doesn't fall eventually on the optimal path to the goal, you wasted your effort. Right? But then, of course, you can't completely avoid wasting. That's why it's called search. Okay, so the interesting thing is that if you have h equal to h star, then these would be essentially straight lines directly going to the goal. So they'll be, they'll only consider the nodes that fall directly on the optimal cost path. And you don't expand anything else. Okay, this is the intuition. This is the intuition in essence. Okay, now it's great. But for the fact that for this intuition to hold, you need to do a little more to the heuristics. There's nothing wrong with what you learned about heuristics till now. If they're admissible, you are guaranteed to be optimal. Except, unlike in uniform cost search, where G can only keep increasing, okay? One question that you have to ask yourself is, now you're no longer talking about G, you're talking about F. Where F is G plus H, where H is an estimate on H star. H star would be fine, but an estimate on H star can be all over the place while still being below H star. What if you are being inconsistent in estimating how much work is to do? Okay, in particular, consider something like this. Suppose I'm at A, then I'm at B, so I went from A to B, so M0A to M1B, okay? And let's say the heuristic, the G to come here is 3, G is 3. So the cost to come from A to B is 3, so G of B is 3, and let's say H is 12. Okay, let's say actually that the optimal goal from B to the nearest goal is 20. I'll show you an example in a minute, but imagine that the closest goal to B is 20. So if I say H equal to 12, I'm fine, right? Admissible. Now suppose I expanded B, I got C. What if I had, so suppose this is another 2. So now G will be 5. What if I have H equal to 1? Am I wrong in calling H equal to 1 in terms of admissibility? No. Then what happens? F of B is equal to 15. F of C, on the other hand, is 6. So apparently, by going to C, the total, so notice the interesting thing. I mean, if I said by, from B, H value is 12, for C, H value can be less than 12. In fact, it should be less than 12. But the question is, it can't be too much less than 12. Because F is not about the leftover distance, but it is the best cost path through B. So if you're being consistent about your estimates, F of B is saying the very best path that you can get from A to goal via B will be at least 15 units costly. And now you are saying the very best path you can get from A to G via B and C will only be 6 units or more. That makes no sense. Do you understand what I'm saying? That makes no sense. Okay? And the reason this is doable is because heuristics are just estimates. And you can be inconsistent in your estimates. And if you have inconsistent estimates, then the F value doesn't keep on monotonically increasing. So in fact, for this picture to hold, it should be the case that a node that A star expands should always have an F value that is equal to or higher than any previous node it has expanded. Otherwise, it's going back. In this case, in fact, you've got to expand this. And when you expand this, you actually are doing an F value that is lower than the previous F value. But then this makes no sense, right? So it's like I'm saying, another way of saying it is, I'm saying, if you want to go from here to Los Angeles via Blythe, you'll at least travel 500 miles. And then I say, if you want to go to Los Angeles from here via Blythe and Reading, I think Reading comes after Blythe, you will at least travel 400 miles. That makes no sense. You're still going through Blythe. So you should at least be 500 or more. I'm theoretically correct, but practically I'm making nonsensical statements. So then you would say, hey, I think you don't know what you're talking about. In this case, since you said the best path that goes to Los Angeles via Blythe is at least 500, when I take Blythe as well as Reading, if I get 400, I take the maximum of that and just Blythe. And I use that as the real value. So if I had said that way, if I had said if you must go through Reading as well as Blythe, you will at least take 550, then maximum 550 and 500 is still 550. Whereas if I was brain dead and said, if you go through 2 cities, you will have cheaper cost than going through 1 city to go to Los Angeles, then you would ignore me, take max of the parent's F value and the child's F value to decide the F value of the child. This is called pathmax correction. And there is no, the thing about pathmax correction is 2 points you want to understand. One is, it is very much possible to be inconsistent in your estimates. People, especially, in fact, cognitively, people are always inconsistent in their estimates. I mean, there's entire books written on cognitive psychology as to how people sometimes think doing 2 things would be sometimes easier than doing 1 thing. Okay? But when you come up with estimates, since we come up with these estimates, we can also be wrong. We can be admissible, still inconsistent. And if you don't have a consistent heuristic, you can make it more consistent by ensuring pathmax. You just say max of your F value and your parent's F value is your F value. You can't have a better F value than your parent. This looks very un-American, okay, but it's not. Okay? I mean, all we are saying is the path that goes through both your parent and you cannot be cheaper than the path that just goes through your parent. Okay? If you were to do the pathmax, in some sense, you are thinking pathmax has been done. When you think of heuristics, you assume heuristics are like distances. Distances obviously have this property, have the consistency property. In particular, it turns out, so this is actually a fixture. Let me go through this also. That's the same thing, but I'm saying it here again. So in this case, I have a little graph, 0.1, 0.1, 0.1, and 25, and 9. Those are the costs of the edges. Okay, so if I give you the heuristic, remember if I give you a heuristic, I have to give the heuristic for every node. Right? So suppose this is 7, 20, 28, 25, 0. Is that admissible? Why? Because C, basically I have 28 and it's only 25.1. Okay, How about this, green? 7, 8.8, 0, 25, and 0. Is it admissible or not? Why is it not admissible? What?
It is admissible.
No. Again, remember I asked admissibility.
Yes.
Is it admissible?
Yes.
Yes. But since you are thinking about this example, you also realize it's a silly heuristic. Okay? It's an admissible heuristic, but it's inconsistent. Why? Because the f value here would be 8.8 plus 0.1. F value here would be 0.2. And so f value of this guy is much less than the f value of its parent. Then if you do pathmax correction, and you say your f value cannot be better than your parent's f value. So max of your f value and your parent's f value is your f value. Then it will be fine. Understood? Okay? So this is basically what's saying. So f of b is 8.9, f of c is 0.2. This doesn't make sense. Since we are reducing the estimate of the actual cost of the path A, B, C, D, G to make f star monotonic along the path, because we want to make it monotonic, monotonically increase f value. Clearly on any path, G value will increase monotonically. What guarantees that?
Or negative paths.
Non-negative distances. Right? It can only increase monotonically. But that is not guaranteed for f value because the h comes in. So somehow h should have this additional property for it to be monotonically increasing. The monotonic increase only improves the efficiency. It doesn't affect the optimality. Okay? So when you make it monotonic, then you do this max of the parent and the current estimate of the f value of this node. And when you do that, you make it monotonic because nobody can be less than their parent. You force it. Now, here is an interesting thing. Distances, for something to be called a distance, they normally should satisfy what is called what? A triangle law of inequality. That's how distances are. What's triangle law of inequality? In any triangle, the sum of two sides must be at most equal to or most of the time greater than the third side. That's triangle law of inequality. It turns out that what we are doing is making sure that f becomes a distance measure, so that we are ensuring triangle law of inequality. So that's the picture. So what I drew here is, this is B, C, and G. The cost of B to C is CBC, which is 0.1. Cost of going from B to G is, cost of going via B to B to G is f of B, 8.9. Okay? And cost of going via C is f of C, that's 0.2. In fact, actually, in terms of the triangle, this part is just the h of C and this part is just the h of B. So h of C and h of B and C of BC must satisfy triangle law of inequality. That's exactly what we did here, in essence. These are the distances. Distance estimates may not be distances because you're being inconsistent, and if you make them satisfy triangle law of inequality, they become distances. Okay? If you were to do that, then you will actually be able to think in terms of these contours. This monotonically, very directed, monotonically progressing towards goal contours, which is what makes A star efficient. Okay? So this one is actually showing, so if I do max, what happens? You can try this. Okay. And this example, 25.2, 25.1, 25.0, that turns out to be an admissible heuristic for this problem. And so this picture shows you that when it's admissible, you go directly and just expand only the nodes and the path to the goal. Modulo type breaking. If there are multiple paths of equal, multiple nodes of equal f values, or multiple paths, optimal paths to the goal, then you might expand more nodes. Okay. Okay, we've done this. Any questions until what I just said? The only point about pathmax correction that I want you to understand, it's a subtle point. Heuristics, because they're estimates, they can be optimistic while still being inconsistent. You're being inconsistently optimistic. You are being way more optimistic at the child node than at the parent node. You should have the same degree of optimism. Then you'll be fine. Normally, things like straight line distance on a grid, it would be consistent. But random heuristics you write with hand, it may not be consistent. If you do make it consistent, and most of the time you essentially, then you can actually have this view of A star search making, very directed progress towards the goal. Okay, so let's look at the properties of A star. Is it complete? First of all, I argued, basically all these classes were to argue that yes, it is complete. Is it optimal? Yes, because one simple way they're saying is you cannot expand a higher F value before you expand a lower F value if you do pathmax correction. But even if you don't do pathmax correction, this is not true, but we did a different proof, that will still hold. Do you see what I'm saying? There are many ways of skinning the cat in this case. Okay, so this is actually the most intuitive way of thinking about it. The reason uniform cost search is optimal is because it will never look at nodes which are 3.7 miles away before looking at all the nodes which are 3.699 miles away. And so if it found a goal which is 3.7 miles, then that must be the optimal goal. Otherwise it would have found other goals before. Right? That's the idea. Time. What's the time for A star search? It has two extremes. If heuristic equal to H star, it does n expansions, where n is the number, d expansions, where d is the depth of the solution, depth of the shortest solution. D expansions, where d is the depth of the shortest solution. If the heuristic equal to 0, which is the least informed heuristic you can make, it will just be uniform cost search. So it will do exponential amount of expansions. So it's between exponential and linear number of expansions. So the question is, what is that on average for a random heuristic? Now, the unfortunate thing is, it's if you consider the relative error in H, which is the percentage error in H compared to H star. So for every node, you know the H and H star, let's say, and you have a guarantee saying H has at most 7% lower than H star. Remember, it can never be 7% more than H star, because then it would have been admissible. Okay, it's lower. The question is, what percent lower? Suppose I said 7% lower. Okay, then it's only exponential it's still exponential in the relative error in H times the length of the solution. The relative error is 0, it's exponential in 0, e power 0, which is just constant. So you're still basically going directly to the solution. Okay, so the relative error goes up into the exponent. So the heuristic must be really, really good for A star to be doing non-exponential search. In fact, A star is always doing exponential search. It's just that the best you can expect in this life of search is, if your friend is doing like this, you do like this. And this is the curve that you draw. Don't expect miracles like that. If it looks like a straight line, it's because it's just slowly growing up somewhere beyond. So, you should do some creative editing of the graph so that it sort of looks like a straight line, but it never really is. Okay? So, A star time is exponential in the error with respect to H, which is why it's not just enough to have admissible heuristics. You want admissible heuristics that are as close to H star as possible. But at the same time, never cross H star. You cross H star once, all bets are off. Okay? And the last thing is space. What about space? Does A star take How many nodes does A star keep? If H equal to 0, A star is uniform cost search. That's nothing but breadth first search. That keeps exponential number of nodes. Since you don't know upfront how good your heuristic is, in the worst case, you get worst heuristic too. And so you get actually exponential amount of space for the open queue. Okay? Now, I couldn't help you with this because it's not easy to come up with H star, which is, has relative error very small or 0. Because if it's 0, then it's H star. Okay, by the way, here's an interesting question. Can you do sorting as search? This is a crazy question. I know that in 310 you did sorting and searching. Okay, but can I not write sorting as a search problem? Long time back, once they made me teach 310, and the poor guys were given a sorting algorithm as the first project. Do a sorting algorithm where you start with any arbitrary permutation. The child generator generates a whole bunch of new permutations, and then you have a test saying, is it sorted sequence? If the sequence is sorted, you're done. So you have a child generator function, and you have a test, goal test. So sorting can be written as search. Would you like to write sorting as search? No. Actually, you can write sorting as search. The reason sorting is polynomial is because the H star can be computed in polynomial time. Here is a crazy way of thinking about the world. All of the world is actually doing search. For some search problems, H star can be computed in polynomial time. When you can compute H star in polynomial time, in essence, you can then actually rewrite the algorithm such that the search, it doesn't look like search, but it is doing search. So search is what's called a weak method. A weak method is always applicable. When a stronger method is applicable, you shouldn't use the weak method. Okay? So if you ever find a problem where H star can be computed in polynomial time, you can still use A star search, but you should ask yourself, why am I doing that? This is like, you can break an egg with a sledgehammer, but why? Okay? That's the question. So H star being polynomial is a dead giveaway that the problem under consideration is a polynomial or a tractable problem. So why should you do search? You should be able to write an algorithm, which ends in finite time. Polynomial time. Okay. So I can't really help you with this unless the problem already is polynomial. Because if I can give you H star which is polynomial, then the problem under consideration must have been polynomial to begin with, in which case you shouldn't have been doing search. You should have been doing more direct methods. Most problems you use search because you don't know of their complexity. Oftentimes they're at least NP hard or worse. Okay? While I can't do anything about this, I can certainly do something about the space. Because we do have an idea for space. You can always reduce space of anybody. When did we talk about an idea for reducing space? Iterative deepening depth first search. So you make iterations on the tree, and in each iteration you do what search? In iterative deepening depth first search, you did depth first search. Now I will want to talk about a new search called IDA star search. So we talked about IDDFS, which happened to do depth first search in each iteration. Okay? So now I want to do IDA star search. There is a tree. So it generates some cutoffs, and each cutoff first you look at this part of the tree, and if you don't find the solution, then you look at this part of the tree. If you don't find the solution, you look at this part of the tree. The whole part again. Okay? In IDDFS, the cutoffs were in terms of depth deep. In IDA star, what do you think will the cutoff be in? Just guess. What does A star care about? F. So these will be in terms of F. Which is why I'm drawing funny shapes. Because F has no connection to depth. So there would be non-uniform shaped iterations, contours. Right? So IDA star would do F value cutoffs, and IDDFS did D value cutoffs. You start from d equal to 0, go 1, 2, etc. Here you start from f equal to 0, then the next higher f value, etc. Okay. Now, in each iteration, IDDFS did a depth first search. So what do you think IDA star should do in each iteration? How many people say A star? Okay. Did I or did I not say, if you go back to the video, when I talked about IDDFS, I said, if you ever want to reduce space and you try to do anything other than depth first search, hit yourself on the head. So please do. I mean, those of you who didn't even speak, you should hit yourself twice, because you probably thought A star didn't want to come out. Okay. This was an entrapment. You know, I was hoping that you would say A star so that I'll say it's not. Not because it's the most obvious mistake to make about this. You know, IDDFS does DFS, IDA star does A star. Nah, that's not true. IDA star also does DFS. Because the only idea we know which gives us linear space is DFS. The only thing that changes between A star and DFS in the iterative versions is one used to do D value cutoffs, this does F value cutoffs. So that's the picture that I'm going to show next. So it's basically IDDFS. IDDFS would work like that, right? Whereas if it is A star, it would talk in terms of F values. So that might be the first F value. That might be the second F value. Notice that the second F value cutoff only allowed one node to come in. Okay, in the case of D, you know how to increase the D. D starts with 0, then 1, then 2, then 3. Because depth only increases in integer values. In the case of F value, how do you know what should be the next F cutoff?
First one in the queue.
Just keep track. Okay, so when you expanded this guy, you know, when originally F equal to 0, then you expand this guy. You get 2 children. Compute their F values. Take the minimum F value that is already higher than the cutoff. That is the minimum you need to expand to get at least one more guy in. If you don't get any more guys in and you keep searching the same thing again and again and again, you don't get completeness. Right? So you just keep track of who is the node that is just falling outside of F cutoff. And that node's F value will now become the new F value cutoff. Right? Okay? So that's the next F value. And so in this tree, I would do depth first search. If it doesn't work, then maybe it would look like this. So this node, this node, this node, this node are in the tree. But I only do depth first search. Not A star. Depth first. But the tree itself has been determined by F values. Okay? And then that, maybe, right? So basically, IDA star does non-uniform contours, and each contour, it does depth first search. If you do this, you're guaranteed linear space. Now the only question is, IDDFS was also asymptotically the same as DFS. We talked about this. Because the number of iterations IDDFS did is at most D, which means the number of times any node is expanded repeatedly is D times. This guy will be expanded D times, this will be expanded D minus 1 times, and so on. What about IDA star? What is the maximum number of times you can expand a node in IDA star? It could be as many as the number of nodes in the tree. Because remember, everybody wants to be unique. If every node has a unique F value, then every time you open the door, one node comes in. Okay? And so you're going to wind up expanding the first guy as many times as there are nodes in the tree. And there are B power D nodes in the tree. So instead of having D iterations, IDA star can do B power D iterations. Not good. Uniqueness is not good. This is why we put you into A, B, C, D, E, rather than you get your name's grade, you get your name's grade, because then you'll all be unique and we don't know how to deal with it. Okay, so you put them into equivalence classes so that when f is expanded, whole bunch of nodes come in. That's how you cut down the number of iterations. So an interesting thing, if I say, suppose you have a heuristic with respect to which you're doing IDA star. I add to this heuristic a small random noise while ensuring that its admissibility holds. I'm adding, so H becomes bigger, and it's still admissible. My question is, how does A star do on this? It should do better. How does IDA star do on this? It should die an ignominious death. Right? Because I'm adding a random noise. So everybody will now have a unique F value. And so when you open the door, you're opening the door like epsilon each, and one node comes in. And so you would be happily doing as many iterations as there are number of nodes in the tree, and you die. IDA star is a great idea, but it works mostly when, in fact, the number of distinct F values is bounded. Okay? That's a pretty subtle point. Okay? We'll stop here.